Thank you so much for the invitation and the introduction. Very happy to be talking to all of you. Um, yeah, and thanks to all of you for being here. So I will talk about Sylvester-Gallai configurations and polynomial identity testing. Um, so this part kind of originated in combinatorial geometry, and this part is from like algebraic complexity theory or computer science, and sort of they are related via some algebraic geometry, which I will talk about. Okay, so I'll talk about all three of those things. So I want to start with the classical question, which goes back a long way to 1893, when Sylvester asked this question. So let's say inside of R2, I have a finite set of points. And let's say my V1 up to Vm is this set of points. So this finite set of points, let's suppose that they have the following property, that suppose, is this big enough for people to read? Okay. So suppose whenever I choose 2 points from my set, there is a third point on the line joining those 2 points. So suppose that for all Vi, Vj, and let's say they're all like distinct points, right? For all Vi, Vj, where I not equal to j, there exists a third point Vk, which is not equal to Vi or Vj, such that when I take the line joining Vi, Vj, L, Vi, Vj, this contains the third point Vk. Okay, so what's happening is we have R2 and I have a bunch of points. Whenever I take a point V1 and V2, I join the line. There should be a third point V3 from my set on this. And maybe there is one more point V4. If I join these two, there should be a point V5. If I join these two, there should be V6. And for each thing, there should be points. Yeah. Now, the question Sylvester asked is that, can this really happen in a finite configuration if all the points are not collinear? So Sylvester's question was that, does this imply are all points of F collinear? Meaning they determine only one line. Okay, so that was the question. And the answer to this question is yes. They have to be collinear. And this was actually, this question was also independently asked by Erdos. And so there are two people who this is attributed to the solution. One is Melchior, who solved it in response to Sylvester's question, and Gallai solved it in response to Erdős's question. They had no idea that this was asked earlier or proved. So this is like 1940 and 1944. Okay. So, but now this theorem is known as the Sylvester-Gallai theorem, which we abbreviated as SG. Okay, so this is the Sylvester-Gallai theorem, and this is not very hard to prove in this case. So, what's the idea for the proof? Yeah, here, let me do the idea here. Okay, so you can really show this using high school Euclidean geometry. Is okay, so you look at the pairs of points and lines. Let's say like V comma L, where L is determined by some Vi, Vj, and this is some Vk, right? So you look at all such pairs of points and lines determined by our configuration, and then you choose the pair with smallest distance. Okay, so without loss of generality, let's assume these are V1, V2, V3. So the line joining V1 and V2, suppose that this line and the point V3 is the pair which has the smallest distance among all possible these pairs. Okay, so this is the smallest distance in my configuration. Okay, smallest non-zero distance. Yeah, so minimum non-zero um, distance. Yeah, if all of them are zero, they're all on the same line. So if they're not collinear, there will be some smallest minimum non-zero distance. So we choose that. And now this line, by the condition, is supposed to have one more point, right? So there'll be another point V4 on this line, and it will be on some side of this perpendicular. So maybe let's say the V4 is here. Yeah. Now, if you join this line, you will see that this distance is smaller. So that's a contradiction. Yeah. So that gives us a contradiction. And so that means that they all had to be collinear. Okay. So this has a really simple argument. Okay. So yeah, any questions? Yeah, actually not. They use more involved and complicated things, which is not bad because they are all kind of generalizable in different ways in different settings. So that's why those arguments are still interesting. But I'm not sure who this is due to. But I mean, this is really sorry. Yeah, probably. Yeah. Yeah. For me, this is from Wikipedia. So okay. All right. So this happened a long time ago, and then later there have been lots of developments of these kind of theorems. So what's the slogan here is that we should think of such sets of points at Sylvester-Gallai configurations. These were just points in R2, but the way we should think of this as some finite set of geometric objects. Okay, and which have some local constraints, just like these local dependencies. Yeah, with local constraints. Okay, and this is all in quotes that in different situations these will be different kinds of local constraints. And the Sylvester-Gallai type questions or the Sylvester-Gallai type theorems, they all say that there is a global constraint on this configuration. Just like these local constraints implied that globally they have to be constrained to be inside of a line. So SG type theorems, they all kind of say that there is a global constraint. Okay. Yeah. So this is sort of the the underlying theme of the theorems in this area. So I want to summarize and make a table of further generalizations of this classical theorem. So where should I do this? Let's do it here. Okay, so the way we can summarize all of this is let's do it this way. So all of these Sylvester-Gallai theorems, they will be happening inside of some ambient space. Okay. And then we will have F, which is our finite set of geometric objects. Okay. And there will be some local constraints. And there will be some kind of global constraint which comes out of these local things. Okay, so some kind of global bound. Okay, so the first example we looked at, our ambient space is R2, yeah, and we have finite set of points, yeah, and the local constraint was there exists Vk in the line joining Vi and Vj, for I not equal to j and k is a different thing. So in this case, you get that they're all collinear. So the affine dimension is less or equal to 1. Yeah. So that's the global constraint we get. We also know that we can do the same thing inside of Cn or Rn, where instead of points, I take a finite set of vectors. Okay. So finite set of vectors. So finite set of vectors is my geometric object. And this local constraint, I can just replace this as Vk is in the span of the vectors Vi, Vj. Okay. So there exists Vk inside the linear span. So this is my notation for linear span in the vector space. So what does this mean? Whenever I choose two different vectors from my set, there's a third one in the span of these two vectors. So under this condition, you can actually show that the dimension of the span of all of F has to be less or equal to 3. Yeah. So this question, okay, so this is over complex numbers. So this is the theorem over complex numbers. Over real numbers, it's a bit better. Dimension of span of F is less or equal to 2 for Rn. Okay. So this thing follows from this thing, but the first one by doing projections. It was asked by JP Sayre at some point that what about complex numbers? And in complex numbers, there are actually examples which show you that they don't have to be collinear, but their span can at most be 3-dimensional linear span, or the affine dimension can be at most 2. Yeah, so that's the theorem here. And this is the one which was proven by Kelly for the complex one in response to Sayre's question. And Kelly's theorem is almost an immediate consequence of the work of Hirzebruch, who was an algebraic geometer, and he studied point line configurations on the projective plane and studied the combinatorics using deep results from algebraic geometry. So this theorem actually uses some deep algebraic geometry, but we will not talk about that today. So the point is that over Cn, this kind of stuff still holds. Okay, any question? Yeah. Okay, what other kinds of theorems are there? So inside of Cn, again, we can take a finite set of vectors. And so this is called the robust version of the Sylvester-Gallai theorem. So here you see, I could think of it like this. I take one vector Vi, then for all the other Vj's, there are Vk's which are in the spans, right? So this third one is a relaxation of that. For every vector Vi, I'm just going to require that there is a delta fraction of rest of the Vj's which contain a third one in the span. Okay, so for all Vi, there exists delta fraction of Vj's such that there exists Vk in the span of Vi, Vj. Okay, if you take delta equal to 1, you get back the previous case. Yeah, so in this case, again, you can prove this is a theorem of Barak, David, Wigderson, and Yehudiaf. This is in 2011, and this is completely linear algebraic and like, yeah, they are computer scientists, so it's quite elementary compared to the other one, and it's actually a generalization of this. It provides a new proof. So this tells you that dimension of the span of F in this case is less or equal to something like 13 over delta square. It will depend on this parameter delta. This has been further improved, but that at least shows us that from these local constraints, you get a global constraint. Okay, question? Okay. All right. And one more. Inside of Cn, again, we're going to take vectors, but the way we're going to take vectors is they will be partitioned into 3 sets of vectors. Maybe the red set of vectors, and okay, and the colors are not important. So if we cannot distinguish the colors, it won't be a big deal. So I just want to write down red and then maybe green, and I have blue. Okay. So our vectors are partitioned in three sets of vectors: the first colored vectors, second colored vectors, and third colored vectors. Yeah. And the local condition, we are going to assume that whenever I pick a first colored vector or a red vector, or and a second colored vector, a blue vector, there is a third colored vector which is in their span. Yeah, so every kind of monochromatic line contains a third color. So there exists Vk in the span of Vi, Vj intersected with the last color. Okay, and you assume this for all possible. If I choose a blue and green, then there should be a red one on the span and so on. And even in this case, you get, this is the Edelstein-Kelly theorem. This tells us that even in this case, you get that dimension of F is less or equal to 3. Yeah. So maybe I should call it something else, like bichromatic. Then it will have to be trichromatic or something. Yeah. 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 Okay. Yeah, thanks. Okay. Other questions? Okay. So the upshot of all of these theorems is this principle that we have some finite set of geometric objects which have local constraints, they give rise to global constraints. Okay. All right. Now, one thing we should note here is that all of this is happening in the realm of linear algebra. Okay, and these are all the constraints are linear algebraic constraints. Okay, so here, so maybe let's summarize here that we have linear algebraic constraints. Okay, so today I want to talk about a different kind of Sylvester-Gallai configuration, which is a non-linear Sylvester-Gallai configuration. Yeah. So the objects we will consider will not be vectors anymore; they will be polynomials, and the local constraints we will put will be a non-linear dependence. And then we'll still ask: is there some kind of global bound on this whole configuration? Okay. All right. Okay. So let me write it here. Let's erase this thing a little bit. Okay. So for the nonlinear one, the one we will consider, what will be our ambient space? The ambient space, for example, will be C x1 up to xn. Yeah. Polynomials in n variables. And it will be a finite set of polynomials, f1 up to fm. Let's say they're homogeneous, and maybe I fix the degree less or equal to d. Okay, so we take homogeneous polynomials with degree less or equal to d. And the local constraints we're going to put is some kind of intersection property, or I'm going to explain this more, but let's put it here that we're going to put radical membership. Okay, so I'm going to write down general definition in a. Mhm. Um, you mean a better bound than for colored with delta? Yeah, I'm not sure if this is somewhere, but there should be. I mean, this is the best possible bound, I suppose, because you can write down examples that you cannot do better than 3. But with delta, I mean, you will probably get some kind of bound, but I'm not sure if it's already proven. But there should be. Yeah, so I feel like this thing, for me, this thing is a little bit more difficult because, right, if I'm in this setting, I can compare all possible pairs. That gives me a lot of freedom. But here I can only compare from these two distinct things, so it's a little bit more constrained. Yeah. Okay. Other questions? Okay. And then we're going to ask, is there some kind of global bound? Yeah. Okay. So let me write down what are these nonlinear Sylvester-Gallai configurations, and then I'll explain what kind of bounds we get and what is it used for, why is it interesting. Okay. Here, yeah, I'm going to write down the exact definition now, and we'll do an example. So the kind of nonlinear Sylvester-Gallai configuration we are going to consider. So let's write down the definition. So we will call it a radical Sylvester-Gallai configuration. Okay, so what's the definition? So for me, like, we'll set S to be our polynomial ring. And what's a radical Sylvester-Gallai configuration? So for this, we also fix some integer d greater or equal to 1. So a set F of polynomials, f1 up to fm, they are homogeneous, and degree fi, they are all of degree at most d. That fixed, that highest degree is fixed. They can be of degree at most d. So we have a bunch of polynomials like this. And what are the conditions? So first of all, we wanted the points to be distinct, so, or the vectors to be distinct or not scalar multiples of each other. So we're going to assume a similar thing here. And let's also assume that they're irreducible polynomials. It's not completely necessary, but let's do this. And so then they are fi, fj are not scalar multiples of each other. Not scalar multiples. For I not equal to j. Okay, so we really have essentially distinct zero sets. Okay, and the main condition, which is the local constraint, is going to be this, that for all fi, fj, I not equal to j, there exists a third one, fk, from my set, such that this thing belongs to the radical of fi, fj, this ideal. This is the radical. And I'm going to talk about what does this mean now. Yeah, so that's our local constraint. Okay, so let's write down here what does this thing really mean. Yeah. So if I have radicals, so given two polynomials, if I have a polynomial f and g, the radical of this ideal f and f comma g, this is the set of all polynomials, so that some power of that can be written as af plus bg. Yeah, so this is the set of all polynomials h, such that h to the power some d is equal to af plus bg for some d, some integer d. Yeah, and a, b are polynomials in our polynomial. Okay, so that's the, if I just had h, that would be the ideal generated by f and g. If I just require that some power is in this ideal, that's the radical. That set of, the set of all such polynomials is the radical. Okay, so how can we think of this geometrically? Is, let's think about this. If h, so remark is that if I have polynomials, I can look at their zero sets inside C to the n. Yeah, so I can look at the zero set. So if I have h inside of radical of f and g, then if I have an input from Cn, like p belongs to Cn, and suppose f of p is equal to 0 and g of p is also equal to 0. So if I have an input where f and g both vanish, this equation tells me h also has to vanish. Yeah. So then h of p is also equal to 0. So what does this mean? This means that if I look at, this is the notation, like v of f, this is the zero set of all zeros of f inside of Cn. Yeah, set of all zeros. This is the hypersurface defined by this polynomial f. the intersection of VF and VG is contained inside the zero set of H. Okay, and all of this is happening inside the ambient space Cn. Okay, so this is one implication, but the interesting thing is that this is also equivalent due to Hilbert's Nullstellensatz. Yes, this is really a classical theorem in algebraic geometry, which kickstarted classical algebraic geometry kind of. So if we could equivalently think of this local constraint geometrically, is that I have bunch of polynomials. They give me bunch of hypersurfaces or zero sets. For example, in R2, I could have bunch of circles, ellipses, and so on. They would be my finite set of geometric objects. And the local constraint is that whenever I pick two of my ellipses, there is a third one which passes through the 4 intersection points, or whatever the number of intersection points are there. Okay, so the intersection of Fi and Fj must be contained inside the zero set of Fk. That's the local constraint. Okay, good. So that's a radical Sylvester-Gallai configuration, and we will call it a. So then, if this happens, then we say that this set of polynomials is a D radical Sylvester-Gallai configuration. Yeah? And this D signifies the degree of the polynomials we are taking. Okay, questions? Yeah, it does. Yeah. So all the, I mean, this one, and this one also, all of them can be specialized from polynomials. If you take degree 1 polynomials, we can recover those things. Okay. So, yeah. So what do I want to do now is maybe some remarks and examples, and then our theorem. Yeah. So let's do it here. Okay, let's do it here. So, first of all, okay, so example 1, let's take D is equal to 1. Yeah. So I'm only looking at homogeneous linear forms. So there are a bunch of hyperplanes inside of Cn. Yeah, they're zero sets. So if I take D equal to 1, what are we asking? We're asking that Lk, these are my linear forms. Lk is in the radical of Li, Lj. Okay, but for linear forms, what happens is that, well, this ideal ends up becoming a prime ideal. So for linear forms, this is equivalent to Lk being in the span of Li, Lj. Okay, so okay, because yeah, if the power of a linear form vanishes on these things, then you can show that this is equivalent. So this means that if I think of L1 up to Ln as sitting inside of, you take this polynomial ring and you take the degree 1 part, which is the all linear forms. This would be equal to the span of x1 up to xn, all the variables. Right? If you take C linear combinations of these things, you get linear forms. So these linear forms are sitting inside of this n-dimensional vector space, which I can identify with Cn. Okay, and the condition, the radical condition, just specializes to the linear condition. This requires a proof, but let's take it for granted for now, that the radical condition for linear forms is equivalent to the span condition. So then it really gives me a linear SG config in Cn, because under this identification, my linear forms are my vectors and I have a span dependence. Okay, so the linear theorem would tell me the dimension of span of all of these is at most 3 by that theorem. Okay, question? Okay, so now let's do an example which is not of degree 1. Okay, so example 2. So I'm just going to write down a bunch of polynomials, which will form my configuration. And the idea is that, so let's fix some number m greater than equal to 6. And my first polynomial is just going to be, and my polynomial ring will be C, X, Y, Z, a 3-variable polynomial ring. Okay. My first polynomial is X, second polynomial is Y, third polynomial is XZ plus Y squared, and my fourth polynomial is X times XZ plus Y squared plus Y cubed. And you see that they're all homogeneous of degree 1, degree 2, degree 3, homogeneous. And the next ones I'm going to generate by mimicking the proof of like infinite, there are infinite many primes, right? You multiply all the primes and plus 1. So do a similar thing here, is that for Fk, we are going to write it as you take the product from F3, F4, F5, dot, 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 Fk minus 1. So define the kth one inductively, and you add the correct power of y to make it homogeneous. So this would be sum over the degree of the previous fi's, I equal to 1 up to, oops, 3 up to k minus 1. So I just add the correct power to make it homogeneous. You have all terms have same degree. So this is my Fk. Yeah. And this example, I mean, the polynomials are not very illuminating, but the point here to make is that this is a radical SG configuration. This is a D radical SG configuration. You can check, you can actually compute, what's the radical of X and Fk? It will be XY. So you can compute those things, and you can see that it actually satisfies these intersection properties. So it's a radical Sylvester-Gallai configuration. And what's the highest degree of the last one? If I have m number of polynomials, then for m polynomials, the degree, they keep increasing, right? The first two have degree 1. So degrees are 1, 1, 2, 3, and then they keep increasing. And the degree of Fm, this will be something like, this is at least, this is around like 2 to the m or something, approximately. Okay. So the degree is approximately 2 to the m. Yeah. And you will see that each one is like from here on, they will all have distinct degrees. So if I compute the dimension of the span, how large can the dimension be? So dimension of span of F will be kind of approximately, this will be at least log D. Because the dimension of the span will be like exactly m, because they are all linearly independent. So what does this mean? In the degree 1 case, we got a constant bound of that dimension is at most 3 by the classical theorem. But in higher degree, I have an example here where the dimension of the span is at least log D. So this means whatever kind of global bound we require, it must depend on D. It cannot be independent of D. Yeah. So, and that is exactly our theorem, that this result generalizes to these radical Sylvester-Gallai configurations. So let me write that down here, and then I'll explain why is it important, what are the applications and ideas. Okay, question. All right. So what's a theorem here? So this theorem of Rafael Oliveira and myself. So what's the theorem? Is that it works more general over algebraically closed fields of characteristic 0. But let's just yeah. So let's write K is some algebraically closed field and characteristic 0. Okay. And what we are going to show is that no matter which Sylvester-Gallai configuration you take, how large, how many variables you had, what field you're over, all those things are irrelevant. You can always bound the dimension of the span of these Sylvester-Gallai configurations by a function only of D. Yeah. So that's the claim, is that there exists a function lambda. Okay, so this would be input would be d, it will spit out some number, such that if f inside of this polynomial ring x1 up to xn is a d-radical Sylvester-Gallai configuration, then the dimension of the span of f, this is the k span for this thing, is at most this function lambda of d. Okay. Question? Yeah. Yeah. Oh, sorry, where? Yeah, it's like it's the same bound you can get for all algebraically closed fields. Yeah, you can do that. Yeah. Yeah, you can formally, yeah, for any algebraically closed field. And if you, yeah, yeah, I think so if you know it for complex numbers, you can deduce it for all algebraically closed fields of characteristic 0. And but the way we prove it, there is really no need to assume complex numbers. We don't use the geometry, so we can work over algebraic closed fields. And yeah, yeah. And if you know it over algebraic closed fields, you will get a bound over non-closed fields in characteristic 0. So that's also follows from this. Okay, so now I wanna do some remarks to explain this theorem and why is it interesting and what does it do in practice. Okay, so yeah, so that's a good question. So right now, I would like to think of it as an existential bound, because if we compute this, the bound that comes out of our thing is like a tower of exponentials, whereas the example is at least log d. And there you can probably make it a bit better, but I think this is kind of the best example I can write down, log d. So there is a huge gap between this example and the bound we get out of this. So because this is tower of exponentials, I just like to think of it as an existential bound. But that is enough for the applications that we want. Okay. So remark 0, the first one is that these Sylvester-Gallai theorems, they are not true in characteristic P. Okay, so not true in characteristic P, because what you can do is even the linear one is not true. Yeah, so even linear SG fails. Why is that? You can just take your set F to be all of like FP to the power n. Yeah, where P is maybe some prime larger than 3 or so. So if you do this, all the points in your vector space is a finite set of vectors. And whenever you draw a line joining 2 points, it will have a third point because there are at least p many points on your line. Yeah. So this fails, and you see the dimension is actually n, which is not 3, which was the bound in the characteristic 0 over complex numbers. Okay, so this theorem similarly, it does not work for characteristic P. Okay, and number 1, what is the, like, why is this theorem, I don't know, like, why is it non-trivial, right? So the point we should note here is that the bound is independent of the field, independent of the number of variables you had, and it's also independent of the number of polynomials we had. It just depends on the degree. Yeah. So similar to the classical case, it didn't matter if I was in a 1,000-dimensional vector space. I had 10,000 vectors, and they satisfied these local conditions. They would always be inside of a 3-dimensional subspace. That's the classical theorem. Here again, it says that if I have in a 1,000-variable polynomial ring and I have 10,000 polynomials, as long as they satisfy this condition, maybe degree is at most 5, then their span will be bounded by lambda of 5. Okay, so the bound is independent of the field, number of variables, and the cardinality of F. Okay, question? Yeah. Yes, that would follow from a linear algebra fact, because we can compute how many monomials of degree d are there. That would be like n plus d choose d or something. And that would be a bound on dimension of that. Yeah. Okay. Yeah. Questions? Okay. So that's why this is interesting. This is non-trivial. And the other thing this thing does is it resolves the conjecture of Gupta. So this solves Gupta's conjecture, which was made in 2014. And this precise statement, Gupta essentially conjectured that, F should depend on low number of variables somehow, should depend on small number of variables. And that you can algebraically, you can say that, okay, like how many algebraically independent polynomials are there? That should be at most some function of D. Yeah. So the transcendence degree of this configuration over this field K has to be bounded by maybe some other function lambda prime of D. So this content, that small number of variables, is exactly made precise by this algebraic statement. But this thing, Gupta's conjecture, actually follows from the stronger statement. If your vector space span is bounded by lambda d, the number of algebraically independent polynomials you can have, that will also be at most lambda d. Yeah. So actually, like this theorem implies Gupta's thing. So this is implied by our theorem. Okay. Yeah. Question? Okay, good. So I have like 6 minutes or something, 7 minutes. Okay. Questions? Okay, now I want to talk about why is this theorem interesting and why did Gupta conjecture this? So Gupta was a computer scientist. So they conjectured this kind of statement to solve the polynomial identity testing problem. Okay. So let me explain that here. And what's the idea? Well, he's no longer in academia, but he's very well and he's working. Okay, so now I explain this PIT. Um, okay, good. So what's the polynomial identity testing? So the kind of questions, like, so this problem, polynomial identity testing, is really central to algebraic complexity theory and all of computer science some way. So the problem is that, given a circuit that computes a polynomial function, a polynomial p, and maybe in these variables x1 up to xn, test whether this polynomial p was identically 0 or not. Yeah. So what's a circuit? It's some kind of, like, you can do x1, x2, 1. These are my inputs, and they are kind of joined by these addition multiplication gates. So maybe you add here, and maybe you multiply here, and then maybe you multiply here. So what this would do is do x2 plus 1, x1 times x2, and then final multiplication gate. So it multiplies them. So it computes this kind of polynomial. So it's an algebraic model for computing polynomial functions. And the kind of questions people are interested in complexity theory is, what is the smallest size of circuit that can compute a polynomial? So there are these VP, VNP classes, which are algebraic analogs of P and NP. And there are these separation questions, which have connections with this PIT problem. So the problem here is that to devise an algorithm which works in polynomial time. So what is the problem? Is we want a polytime algorithm for doing this polynomial identity test. And this should be polynomial in the size of the circuit, which is the number of edges you have in this directed acyclic graph. Okay, all right. Okay, good. So that's the problem. For example, you might have some kind of a circuit which is computing this polynomial, x times x plus y minus x square minus xy. If its circuit spit out this polynomial is actually identically zero. Right? So you want to figure out whether your circuit was computing identically zero polynomial or not. There are many reasons this thing is important. Is, for example, if you have, first of all, let me say that there are efficient randomized algorithms which run in polynomial time, but we want a deterministic polynomial time algorithm. Okay, and why is this an interesting question? This is really central to algebraic complexity theory, because if you have efficient deterministic PIT algorithms, one thing that it implies is that you can construct explicit hard polynomials. So that has consequences towards VP versus VNP. And the other things is that if you can do this in general, you can solve lots of problems. For example, you can do perfect matching in polynomial time, like determining whether it has perfect matching or not, a graph. You can do the A-case primality testing, which comes via PIT. So primality testing. So what happens is that in a lot of these algorithmic problems, you can formulate it as whether a polynomial vanishes or not. For example, for perfect checking whether a graph has perfect matching or not, you compute the Tutte matrix, and if the determinant of that is zero, it has a perfect matching. Right? So, and that determinant will be a polynomial. So you're trying to test whether that polynomial is identically zero polynomial or not. So lots of problems reduce to this PIT problem. Okay, so that's why it is important. And now let me explain what's the connection with Sylvester-Gallai configuration. So the connection, and why did Gupta conjecture this? So let's do a toy example. Let's say my circuit spit out a polynomial f, which looks like this: p1 dot dot pr plus q1 dot dot qs plus r1 dot dot rt. Yeah, just like this. Maybe there was some product, some sums. It spit out a polynomial like this. And suppose that these all have degree at most d. Yeah, maybe my circuit, this is just an example, maybe my circuit was computing such a polynomial, and I wanted to test whether this polynomial is identically zero or not. Yeah? So let's think about the case. What if this was identically zero? Can we extract some kind of structure out of these polynomials? So if f is identically zero, that means p1 dot dot pr plus q1 qs plus r1 rt is identically zero. Okay, so what kind of conclusions can we get out of this? This whole expression is zero. If you plug in an input into this whole polynomial, it's going to spit out zero because it's identically zero polynomial. So what if I have an input where p1 vanishes and q1 vanishes? Then this goes away, so the product has to vanish, which means that this polynomial vanishes at the zero set of p1 and q1. Yeah. So if p1, q1 vanish at some input x, then the product of the ri's must vanish. Okay. And the way to think of this is a generalization of all the Sylvester-Gallai theorems we saw. It's like a colored. We can think of this as the first colored polynomials, second colored polynomials, and the third colored polynomials. And whenever you pick a first colored polynomial and a second colored polynomial, the product of the third colored polynomials vanishes on their common zero set. So this thing sort of gives me a three colored product, because I don't have just a polynomial, I have the product radical SG config. Okay? And what, this is the last thing I'm going to say, is that what Gupta showed is that if you can, Gupta conjectured a k colored product radical SG conjecture, is that whenever you have k number of colors and these properties, their dimension should be bounded by some function only of d. That was Gupta's conjecture. And he showed that if you have this conjecture, you can get polytime PIT for these kind of circuits. So these are called depth 4 circuits, which is still unknown and very useful. Okay. So this general Sylvester-Gallai theorem will give you polytime. It will solve the PIT problem for depth 4 circuits, which is almost enough to get these kind of results. And as a first step, if this was true, somehow the first challenge is to solve the first conjecture, which is what we solved. And we have other results which show that these work in smaller degrees. And right now we are working on fully resolving this to get PIT, solve the PIT problem completely for depth 4. Okay, so I stop here. Thank you. Yeah. There is in degree 2, which we prove in joint work with me, Rafael Oliveira, Avivav Garg, and Sheer Pellet. Or maybe no, she is in the other paper, but yeah, there is a degree. She and some other person, Amir, also proved it. So there is in degree 2, there is a delta version. In degree D, not yet. Yeah. Yeah. Mm-hmm. Yeah. Yeah. So I'm not sure about. I mean, I don't know enough about that right now. But the PIT was definitely in some way it is connected and was used in the PCB kind of thing. And yeah, I think it might be possible. So I really have to think more about it. But yeah, that seems good. Um, yeah, you can actually do this radical non-membership in polynomial time. You can check whether Mm, yeah. So it's no, yeah. I have to understand your question more. To think about it. Yeah. Mhm, mhm, mhm. Yeah, that's how we are using locality. Yeah. Yeah, it should take care of all the variables. Yeah, yeah. Mhm, 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 mhm. Yeah, that's a good question. Yeah, I didn't say anything about the techniques we use. Yeah, so it's algebraic geometric, because this radical condition is no longer linear, and yeah, and at least we cannot get a linear algebraic proof, and I would assume not, because yeah, this is it is kind of, so it's kind of like these coefficients that you get in the equation, you have to control those polynomials. But in the notion, I mean, that radical equation, those coefficient a and b polynomials, they can be pretty much arbitrary. So it's really hard to control them. Yeah, the degree is bounded by effectiveness cylinders. But so that is one thing we thought about. But like to control the coefficient, you can write down examples where the coefficients are pretty much arbitrary. They have no connection with my configuration of original polynomials. So then it becomes hard to control those polynomials. So it's really algebraic geometric. It's not algebraic geometric in the way the classical proof of Kelly was, but it's a different kind of algebraic geometry. So the one thing, the main perspective is from commutative algebra to use something called to connect it with the Stillman, the uniformity principle in commutative algebra, which I will just summarize in this way, is that, if I have an n variable polynomial ring, and I keep taking polynomials in these polynomial rings, if n is very large, the polynomials will become more and more complex. Okay, so million variable polynomial is intuitively, as we would think, is more complicated than a 5 variable polynomial. Yeah, but the thing is that if you fix the number of polynomials you're looking at, if I'm looking at only 10 polynomials and of degree 5, whether it's in 100 variables or 1000 variables, a lot of the geometry is still bounded. And that is something which happens in commutative algebra. It was a recent breakthrough. They proved some conjecture, and we connected to that, and we build upon those recent results to develop it more, to combine with combinatorics and to prove this result. So in some sense, in algebraic geometry, there are things which will help you get rid of n and k, the dependence, but it does not help you get rid of the number of polynomials, which is essential in this problem. So that's a huge difficulty, but that was an inspiration, and that still helps us prove this theorem. Okay, thank you.